for coming back after lunch. Thanks to the organizers for such an interesting workshop, and for everyone for returning to it. Hopefully this will be a fun talk. I have slides for all of the proofs of the claims I'm going to make, but my plan is to skip them unless someone raises their hand and asks for them. So I'm prepared to prove things, but I will not obligate you to see them. So what I want to talk about is something that is at first seemingly unrelated to the themes of the workshop. I'm going to talk about a problem in data analysis that, depending on if you come from a statistics background or a machine learning background, you might know as either overfitting or false discovery. Okay, so this is just a problem in data analysis independent of privacy concerns. But the punchline is going to be that, if you were doing your data analysis with differential privacy guarantees all along, then you've also solved this other problem. So this is a reason to sort of care about differential privacy, even if you are not convinced that the privacy guarantees it gives are necessary for you. Okay. So maybe just to, I'm sure many of you are familiar with overfitting and false discovery already, but maybe just to introduce it, in a fun way for those who aren't. You may have seen an email scam like the following. Okay, so suppose I get an email from someone who asserts that they're a trustworthy stockbroker, and they give me an investment tip. Okay, they say that Shake Shack is a great investment. I should put my money in Shake Shack today because tomorrow the price is going to go up. Okay, so I have no particular reason to trust this person, but I notice the email, and indeed they're right. Price goes up today. Okay, but I'm not too impressed. Dumb luck. And I get another email from them tomorrow, and it says, hey, the price is going to go down today for Shake Shack. Maybe you should take your money out or short the stock. And okay, these are continuing to go in my spam folder, but getting a little curious, and indeed, he's right. The price goes down. And I get another email on the third day. He predicts it's going to go down, and he's right. And on the fourth day, he makes another prediction. It's going to go up, and he's right. And this goes on, and it's getting suspicious. He's right every day. I get 10 of these emails in a row, and every single day, his prediction was correct. Okay? And so at the end of 10 days, I get a solicitation. He says, look, I'm tired of giving you this valuable advice for free. I'm obviously, really good at my job. I was able to predict, without fail, 10 days in a row, the trajectory of this stock. I'll tell you what, why don't I manage your money for you? This is clearly a good idea. And I'll take a small cut. Just give me your financial information. Okay. So, how should I think about this? I mean, okay, I want to think about this as a scientist. There's me. And maybe I want to test the null hypothesis that this guy doesn't, I think this guy was just bullshitting. This guy is flipping a coin every day. He's no better at random guessing about whether stocks are going to go up or down. Okay, so I can compute a p-value. I mean, what's the, under my null hypothesis, the chance that he's right on any day is 1/2 if he's flipping a coin, and the chance that he's right 10 days in a row would be pretty small. It would be 1/2 to the 10th. Okay, and I find, okay, my p-value is less than or equal to 0.05. I can safely reject my null hypothesis, and I give him all my money. Okay? So this, I'm wearing a lab coat. This seems like a valid statistical inference. So where did I go wrong here?
Can I just clarify that that's not a p-value, that's the probability of getting 10 correct.
It's the probability of the observations under my null hypothesis.
Area under the curve.
Under my null hypothesis, the probability of the observations that I saw, 10 correct predictions in a row out of 10, is 1/2 to the 10th. And so if what I'm going to do is reject the null hypothesis when this number is less than or equal to 0.05, then I reject the null hypothesis exactly 5% of the time. So this is a p-value. Okay. Good question. Other questions? Okay. So where did I go wrong? It's not in defining what a p-value is. What I failed to take into account is the size of the possible hypothesis class. Okay, so unbeknownst to me, what was going on behind the scenes is this scammer was not just sending emails to me. He was sending emails to a lot of people. Initially he sent emails to 100,000 people, and for half of them he predicted the stock was going to go up. For half of them he predicted the stock was going to go down. And guess what? One of those two things happened. And the second day he repeated only on the subset of the people for whom he got the answer right. Okay, so on and so forth. And so no matter what happened, he was guaranteed that at the end of 10 days, there were 100 people out there for whom he made perfect predictions and sort of would be misled by their naive estimate of the probability of these events. Okay, so my statistical error when trying to reject the null hypothesis was my failure in taking into account the size of the hypothesis class, the size of the, this is an instance of what you might know as the multiple hypothesis testing problem. My inference was correct if, I was thinking about him communicating only with me, but I failed to correct for the fact that he was communicating with 100,000 people. Okay, so this is not just like a good email scam. If you've been paying attention to sort of the popular science literature recently, you may have come across articles that are hand-wringing about a crisis in empirical science. So this is the cover of an issue of The Economist from earlier this year called "Trouble at the Lab." But there have been a number of articles this year about the same topic. And just to argue for a moment from authority, some quotations by people much more famous than I. John Ioannidis asserts that most published research findings are probably false. A quote from this Economist article, Sandy Pentland says that 3/4 of published scientific papers in the field of machine learning are bunk because of overfitting. And Nature News estimates that irreproducible biology research costs about $28 billion per year. Okay, so the problem in general is that you might hope that when you like read an article in a reputable journal and see that p-values are less than or equal to 0.05, then the fraction of those results that turn out to be wrong should be roughly 5%. But empirically, it seems to be much higher. And there's a lot of reasons for that, and I'm not going to talk about most of them. I mean, there's all sorts of reasons, including fraud and all sorts of social aspects. But I just want to talk about one issue, which is that the statistical theory used is designed for one setting, and the practice of data analysis largely is in a different setting in which that statistical theory does not apply. Okay, so preventing overfitting is, a decades-old subject. People have been worried about this for a long time. There's lots of tools to try to prevent it. There's the simple holdout method. I can, do my model selection on one half of the data set and try to evaluate it on another held out fraction. I can do cross-validation. There's the bootstrap. But all of these methods, and to the extent that there are theorems for these methods, the theorems hold for what I'm going to call static data analysis for the most part. So this is starting to change a little bit in the statistical literature, but this is, for the most part true. And sort of at a cartoon level, static data analysis is maybe what you learned in your Statistics 101 class in 6th grade. I don't know if 6th grade is a meaningful phrase in England, but it's that what you're supposed to do is choose the statistical method that you're going to employ independently of the data. Okay, so choose the kind of regression you're going to run and the model you're going to use independently of the data. Then you gather the data, okay, and then you run your method and you see what the outcome is. And importantly, you are not supposed to, after you see the outcome, go back and revise your model, remove some variables, take the log of some other variables, and try again. Because if you do that, the model will no longer be independent of the data, and you can run into trouble. On the other hand, adaptive data analysis, at least the way I'm going to use the phrase, is talking about exactly this scenario where there is a loop. That is, after I observe something about the data, I go back and decide, to make modifications perhaps to my statistical method. Maybe I'll add a variable. Maybe I'll decide to run an entirely different kind of analysis. And I'll do that, and I'll do it on the same data. And now I have to take into account the fact that my choice of model actually depends on the data I'm using. Okay, so adaptivity is like not a new concept. It's known by many names in the literature, and many of them are not flattering names. So just a list of them, it's sometimes called data dredging, phishing, p-hacking, post hoc analysis. I like Andrew Gelman has an article which calls it the garden of the forking paths because of all of the different choices you might have made given different outcomes of the data.
Before it became respectful, it was called data mining.
Yeah, so one of the negative terms is data mining, but I last gave this talk at ICML, which is a machine learning conference, and data mining is the name of a... I agree with you that that's a disparaging term, but one should not always say that. Okay, and one of the sort of prominent solutions is to just avoid it altogether. Okay, so people advocate for what's called pre-registration, which is essentially just a method to forbid you from doing this. You're supposed to register on, ideally a sort of publicly observable and verifiable website, exactly the procedures you intend to run before you gather the data, the hypotheses you're going to test, so that when I read your paper, I can make sure that the analysis you report is actually the analysis you intended to do and that you didn't change it as a function of the data. Okay?
And in part, this was done also against publication bias.
Mm-hmm.
So that the studies that, some will succeed at random, like your first story, but you never know about them, which is exactly that.
That's right. So this does a couple of things. One is that you might see the existence of, research projects that never end up getting published, which is valuable. But the other is that for the published ones, you know that the analysis they carried out was the analysis they intended to carry out. And both of those are sort of important issues, but I'm only going to focus on the second one. Okay, so that's one solution. I mean, that does solve the problem of adaptivity by eliminating it. But it's a little bit draconian. I mean, because adaptivity is useful. You'd like to be informed by the data. I mean, ideally, as scientists, we learn from the data. That's we want to learn from observing the world. And so we'd like a less sort of constraining method than this that is still statistically safe. Okay, so again, from this nice Gelman and Loken paper called Garden of the Forking Paths, they say, quite rightly, I think, that the most valuable statistical analyses often arise only after an iterative process involving the data. Okay, and that's the sort of thing that is prohibited by pre-registration. Okay. So if we want to develop a theory for how to think about adaptive data analysis, let's first try to just specify some desiderata. Like what are the different kinds of scenarios that we might want to protect against? Okay? So the easiest is, I think, overfitting from fixed and well-defined algorithmic or statistical procedures that we can that make choices as a function of the data but are precisely specified. These are things that we might hope to analyze exactly. Okay, so in my little picture here, you've got your data. Maybe you split it into a training set and a validation set. You fit your model. Maybe this is sort of you've got a linear regression model in mind with some collection of variables, and you fit it. You validate it on the validation set. And then you've got some procedure, maybe like forward stage-wise regression or something like that, that's going to add or remove variables from the model. Okay, so the model will be selected as a function of the data, but in a well-specified way. I can peer into this box and see exactly what the rules are for doing that. That's maybe the easiest thing, because we might hope to analyze this exactly as a static procedure. A little bit harder, but something we might want to deal with as well is what Gelman and Loken call researcher degrees of freedom, which is basically the same thing, except where the model selection procedure is no longer a well-specified algorithmic or statistical procedure, but it's just based on the decisions of the human data analyst. So the human data analyst is seeing the results of the model fitting and making decisions, but not in a way that we can precisely reason about because it's sort of a judgment call. And this happens all the time. So here is just an example from that paper, the Gelman and Loken paper that they point to. This is a study in which researchers are trying to show that some effect holds both on American subjects and Danish subjects. And they run a regression on the Danish subjects and find an effect. They run the same regression on the American subjects and don't, but they say, variables 5 and 6, which were answers to questions on a survey, these questions mean different things to the American subjects, and so we shouldn't include them. And indeed, when they remove those variables, they find the effect on the American population as well, which isn't necessarily something you should call by one of these disparaging terms like data dredging or data mining or p-hacking, because they might have been well-intentioned. But it is a researcher degree of freedom. It's model fitting as a function of the data, and ideally we'd like to be able to report valid p-values after you do that, but if you report valid p-values, if you report p-values while ignoring the fact that you did this, they're not valid. Okay? And here's a third use case we might like to protect against. It's multi-researcher reuse of data sets. And this is sort of the hardest one, I think. So here we've got a researcher who might be employing researcher degrees of freedom himself. And he publishes his paper, and another researcher comes along and reads his paper and says, wasn't that interesting? Could I use your data set? Okay, and researcher 1 is happy to share his data set. And remember, not only is his data being reused, but researcher 2 has read the paper that researcher 1 published. And so researcher 2's hypothesis about the data is not independent of the data. It's a function of the data. It's a function of researcher 1's analysis. Okay, but he's using the same data set, so we have to be careful. And this can continue. This can continue. Researcher 3 can read both of these papers, get the same data set, and perform his own study. Okay, and this also is hard to model and causes problems. As a homework assignment, you can try to find the longest citation chain of papers that use the same data set, if you like. Okay. So if we want to handle these three things, what are some desiderata that we want in a theory? Okay, so first, we want a theory that's flexible enough to analyze all of these kinds of procedures. Okay, so we don't want to analyze only precisely defined algorithmic procedures. We don't want something specific like that. We want maybe a way to think about the information that's leaked about a data set via an analysis, so some kind of information measure. And we want it to be flexible enough to reason about many different kinds of algorithms. Okay? And we'd like it to be robust to post-processing, meaning, not just that the precise results of your study should be safe for use in directly sort of selecting for me, directly selecting a model, but that I should be able to think about the results of your study and extrapolate based on other things that I know, so long as I don't do this based on your data set itself. And we'd like this post-processing to be both precisely defined, for precise algorithmic procedures like stage-wise regression, and imprecisely defined. So we'd like the post-processing to be able to be done by human analysts that we don't well understand. And finally, we'd like graceful degradation under composition, meaning if we have, individual statistical procedures that are safe in some way to be defined, that even if these are composed, even if we have, if we combine them to build more complicated statistical procedures, or we have chains of mutually dependent research projects, each building on one another, so long as every individual researcher uses a statistically safe procedure, we want the entire composition to be statistically safe. These are maybe like the dream list of things we might want. Okay. So there's now exciting literature on this, and there's a growing list of information measures that satisfy these various desiderata. And for the rest of this talk, however, I'm just going to focus on the one you've heard most about this week, which is differential privacy. It turns out that differential privacy has lots of these nice features, and one reason for using differential privacy is to have the sort of guarantees of safe statistical analyses I've been talking about, even if you don't care about privacy. You can think of privacy as just a side benefit, if you like, or vice versa, depending on your perspective. Okay. So in order to state theorems about this, we have to choose a particular mathematical formalism. I'm going to describe a particularly simple one that I'll argue briefly doesn't lose much generality, but I want to point out that this is not the only mathematical formalism you could use to prove these kinds of theorems. So I'm going to talk about a simple formalism that talks about sort of data analysts repeatedly estimating expectations on a distribution. Okay, but if you wanted to, you could talk directly about data analysts correcting p-values in hypothesis testing, for example, and you'd get a similar set of results. And I'll point you at the end. I'll have a bibliography at the end if you prefer a different formalism. You could. I'm not going to talk much about p-values here, but you could read versions of these theorems for p-values. Okay, so I'm going to choose a formalism for convenience to have particularly simple theorems. Okay, so here's the formalism. We're going to have a data universe X, okay? And this is just the space in which your data points live. Okay, so if every data element in your data set is described by d yes or no values or something, then this would just be the set of all 2 to the d possible realizations of data points. And there's some distribution that we don't know over this data universe. This is sort of the population that we'd really like to learn about. We'd like to learn facts about this distribution. Okay, but we don't have direct access to this distribution. That's the problem. That's why we might be at risk of overfitting. The only access we have to the true population, the distribution we care about, is a data set. And the data set is sampled independently. It consists of endpoints sampled independently from this distribution. Okay, so we've got our distribution. We care about this. But what we have is this. It's n point sampled IID from this distribution. Okay? I'm not going to assume anything about what this distribution looks like. The only thing I'm going to assume is that the points in the data set are independent samples. Okay, so what's a statistical query? And we talked about this a little bit already during the sort of differential privacy portion of the week. A statistical query is just some predicate. Okay, it's some function whose average you care about. Okay, and it's a predicate mapping elements in the data universe to numbers between 0 and 1. Okay, so for example, it might be a predicate that evaluates to 1 if you are a resident of New York who has, brown eyes and makes more than $80,000 a year. And the value of a statistical query, the thing that we care about, okay, the value of the query evaluated on the distribution is just the expected value of this predicate on the distribution. It's the fraction of people in the population I care about who live in New York and have brown eyes and make more than $80,000 a year. Okay? But we can't directly evaluate this because we don't have access to the distribution. So instead, we need to find some way of estimating these answers. And so a statistical estimator in the rest of this talk is just going to be an algorithm for trying to estimate the value of a statistical query. Okay, it's going to be parameterized by the data set, since that's the only access we have to the distribution. And given the data set and the query, it will return some answer, some number between 0 and 1. And what we hope is that the value it returns is close to the value we want to know, the value of the query on the distribution. Okay, and just to, this is a simple formalism, but I just want to point out briefly that it doesn't lose that much generality. Okay, so obviously, lots of things are already just expectations, means, variances, correlations between features. If what you care about is the accuracy of some classifier, the risk of a hypothesis, the mean squared error of a linear regression model, that's also just a statistical query. And more importantly, the gradient of a sort of the gradient of the risk of a hypothesis is also a statistical query. So if you want to run a linear regression, well, you can find the regressor by doing gradient descent. Adam talked about this a little bit. And the only thing you need to be able to run gradient descent is access to gradients, and those are just expectations. So you can train convex models using only access to statistical queries. Okay. So what do I mean adaptively chosen statistical queries? Because we want to talk about adaptivity in this model as opposed to static query evaluation. So here's what I mean by adaptively chosen queries. We've got our unknown distribution, okay, from which we've sampled a data set. And we've got a statistical estimator A who has access to this data set. And we've got our data analyst. And the data analyst will interact with the statistical estimator as follows. He'll ask his first query and get his first answer. And now, as a function of the answer to that first query, he can decide on what his second query is going to be. He'll ask his second query, and he'll get his second answer. Okay, and as a function of that second answer and of that first answer, he can decide what his third answer is going to be. Okay, and this will continue, and he'll ask k questions in total. Okay, so the questions he asks at later rounds are functions of the data because they depend on the answers he got in earlier rounds. Okay? And how are we going to evaluate the quality of a statistical estimator? Well, here's a simple measure. I'll say that a statistical estimator is epsilon delta accurate if, for all sequences of k queries that might be asked to it adaptively, and for all data analysts who might have been asking those queries, and for all distributions from which the data might have been drawn, then with high probability, with probability 1 minus delta, if I look at the query that was answered most incorrectly, the query with highest error, the one for which the answer the statistical estimator gave was furthest from the true answer, that should be at most epsilon. Okay? So an epsilon delta accurate statistical estimator with high probability, with probability 1 minus delta, answers all queries correctly up to an error tolerance epsilon. That's going to be the simple measure I'm going to use to evaluate statistical estimator.
For all data analysts, what's the difference?
Well,
Today I'm this, tomorrow I'm that. This quantifier.
What I mean is, I don't want to. I want this guarantee to hold without any assumptions on the data analyst. I don't want to assume that the data analyst is somehow being friendly.
But isn't that contained in the for all the sequences? Oh, you know,
Yeah.
for a specific sequence.
Yeah, I guess this is the name of the quality measure. I'm saying a statistical estimator is accurate for all sequences if, for all data analysts, this holds.
What's the
But you don't need to quantify. We're just quantifying overall data analysts, which implicitly quantifies overall sequences that might be asked. Yeah.
So and it's phi p, not phi original data.
That's exactly right. That's important. What I want is that the statistical estimator should give me answers that are accurate with respect to the distribution, the thing that I care about. If all I wanted to do was get answers that were accurate with respect to the data set, that would be extremely easy. I'd have my statistical estimator just give me the empirical average of the queries on the data set. My accuracy would be perfect, but that wouldn't prevent against overfitting. Overfitting is exactly what happens when you're accurate with respect to the data set, but not the distribution. So it's important here that what I'm demanding is accuracy with respect to the distribution, and this is why it's a little bit of a tricky problem, because the statistical estimator doesn't know the distribution, it only knows the data set.
Is the probability over choices of D?
No. Oh, well, yes. So the probability here is taken over both the randomness of the statistical estimator. The statistical estimator is allowed to flip coins, and over the draw of the data set. So I am assuming that the data set is sampled IID from this distribution.
So the estimator is not deterministic?
The estimator need not be deterministic. And that's going to be an important point. Good. Other questions? Okay. So let's just, as a baseline to figure out what we might hope for, let's think about the easy case, the non-adaptive case. But by this I mean the data analyst will choose all k queries up front before looking at any function of the data. He'll ask them all simultaneously, and the statistical estimator can now just give the answers in one batch back to the data analyst. Okay, so in this case, the obvious thing you would do to construct a statistical estimator works extremely well. Okay, the empirical average mechanism, which just returns for every query the empirical average of that query on the data set, does well. That's because the data set, when the queries are independent of the data, is an unbiased estimator for the expectation of any quantity, because it's sampled IID from the distribution. And when I say it does well, just to plug in some numbers so we have some concrete bounds to compare to, if I want 1% error with probability 99% on all of my queries, then this estimator can answer a number of queries that is exponential in the size of the data set. Okay? So if the queries are non-adaptively chosen, I can answer exponentially many queries in the size of the data set.
I guess I'm missing something, sorry. If I have a random sample of 1,000 people, or 2,000 people, or something,
Yeah.
then the estimator is going to have some uncertainty naturally just from the sampling process.
That's right.
And so to get that down to 0.01 accuracy, I may not be able to even do that, even if you let me have an unfettered, non-p-hacked, whatever value.
That's right. So there are some constants hidden in the exponent. So what you're saying, I think, is that if you have n data points, you should sort of expect sampling error on the order of 1 over square root of n for any query you ask. And if I ask k questions, and they're all independent, by a union bound, I should expect, for the worst one, error something like log k over square root of n. And all I'm doing here is solving for k instead of for n, because the error you get is logarithmic in k and polynomial in n. When I solve for k to ask how many questions can I ask, if I'm happy with 1% error, it is k. It is exponential in constant times n. But there's a constant there, so it's not that if you only have 5 data points, you can necessarily get 1% error at all. Does that make sense? Marco?
When you say, can I ask, what do you mean exactly? I mean, if I just ask one query, I will not have that bound. So
I don't follow. What I'm saying is that, for my statistical estimator, there will be some guarantee about the accuracy for the answers that I give. And there's different ways to parameterize that. I could ask what's the accuracy I get as a function of the number of questions I'm asking. Or just solving for a different variable, I could ask for a maximum error tolerance I'm happy with. What's the maximum number of questions I can ask? This is the same question. I'm just solving for a different variable. And all I'm saying here is that if you're happy with 1% error, and your queries are chosen independently of the data, then you can ask exponentially many.
But k must be exponential.
No. I mean, you could ask fewer questions and still get accurate answers. Other questions? Please ask questions. I mean, it's good to understand these early baseline points so that the future slides are more impressive. Yeah.
It's the other way, as you say, it's a dual, so that if k is less than 1, n isn't large enough to do anything useful. So you need more data.
Well, k is the number of questions you want to ask. So if k is less than 1, you don't want to ask any questions. In that case, you don't need any data.
Or the number that you can answer is what k is.
K here is the maximum number of questions you could get accurate answers for if you wanted, given the amount of data you've got, and the desideratum that you get at most 1% error in your answers.
So if k is less than 1, I can't answer anything.
Exactly. I mean, this is just a Chernoff bound, and I'm solving for the number of questions. Yes.
It's wondering if this is sort of related to something similar. Suppose I was doing some ecological analysis and I wanted to know the fresh air bounds. Then usually you get the fresh air bounds by conditioning on the sort of structure of the table you're dealing with. This would be like fixing the fresh air bounds and saying how big a table do I need, which is basically the number of variables.
So without knowing what Frechet bounds are, I will tentatively say, Cynthia's saying no. I don't know what a Frechet bound is. Maybe we can talk about that later. But are there other questions? Okay. So this is the baseline. And the unfortunate fact is that if I use this empirical average mechanism, then it's not hard to show that if the queries can now be chosen adaptively, and I have the same desire to get answers with 1% error 99% of the time, then now I can't answer more than linearly of them. Okay, so my statistical estimator has gotten worse by an exponential factor. If the queries were non-adaptively chosen, I could answer exponentially many in the size of my data set, but adaptively, I won't get accurate answers necessarily if there are more than linearly many questions. Okay? This is for a particular mechanism. This is for the empirical average mechanism, the sort of first thing you would try. That doesn't mean there aren't better ways to do it. Okay, so the question is, can we do better with a different statistical estimator? Okay, and this is where differential privacy is going to come in. So, you know, many of you probably saw Adam's tutorial, so I won't talk much about differential privacy, but just to remind you about what the definition is, it's a stability condition on the output distribution of the statistical estimator. Okay, so it's got two parameters. Before we called them epsilon and delta, but since I already used epsilon and delta for something else, excuse me for here calling them alpha and beta. Okay, now statistical estimator, well, it's an algorithm. It's possibly a randomized mapping between a data set and some outcome space. And it's alpha beta differentially private if for every pair of neighboring data sets, for every pair of data sets that differ in one data element, and for every observable outcome S, the probability that the outcome occurs when I run my analysis on data set D should be close to the probability that the same outcome occurs when I run my analysis on data set D prime. And close means within an e to the alpha multiplicative factor and a beta additive term. Okay? So it's a stability condition. And crucially for this application, it's a stability condition on the output distribution, not on any metric on the outcome space. This is important because, remember, one of the things we want is sort of good behavior under post-processing, that I shouldn't be able to sort of think, you know, sit in the corner and think about the outcome of a differentially private mechanism and come up with some conclusion that is not differentially private. Okay, you know, if we had a stability condition on the actual outcome space in some metric, I'd be able to do that. But because it's a stability condition on the distribution on outcomes, I cannot do that. Okay. So here's like, you know, suppose you didn't care about accurate statistical estimators. You just wanted to come up with a differentially private way of answering statistical queries on a data set. Here's maybe the first thing you would do. I've got my data analyst. Okay, and for k rounds, what I'm going to let him do is choose a statistical query based on the answers I've previously given him. And I'm going to answer his query by just, you know, noise perturbation. I'm going to compute the exact answer to his query on my data set, the empirical average. But because I want differential privacy, that's not what I'm going to tell him. I'm going to tell him the answer to his query plus some additive Gaussian noise that has standard deviation on the order of square root of k divided by the size of the data set and the privacy parameter. Okay? And this is alpha beta differentially private. Okay, this is just a, you know, simple noise perturbation technique that guarantees differential privacy. And if all I cared about was accuracy with respect to the sample rather than accuracy with respect to the distribution, it would be easy to analyze how accurate this noise perturbation technique was with respect to the sample, because the error I get with respect to the sample is just the maximum magnitude of the noise I ever add. I mean, the error with respect to the sample only comes from this noise. And because the standard deviation of the noise I'm adding is square root of k, and I'm adding it to k questions, the maximum error will be something like the square root of k times log k over the size of the data set. This is accuracy with respect. You're laughing.
because you wrote a whole textbook where alpha and beta were the accuracy, and epsilon and delta were the privacy. And in those formulas, they exactly reversed, so you could have done it here, but you didn't.
Yeah, sorry about that.
Done it right.
Thank you.
When I initially made these slides, I had it the way you're specifying, but I was initially going to give this as a tutorial with someone else, and he insisted that his half of the slides be different. So I did this for consistency. Apologies, I didn't switch it back for this audience. Okay, so you get accuracy with respect to the sample, just because I'm not adding too much noise. Okay, but who cares about accuracy with respect to the sample? I've motivated this whole thing as wanting to prevent overfitting, wanting accuracy with respect to the distribution. Okay, and the punchline is going to be the following. What we have is a transfer theorem that says roughly this. If you have an algorithm, a statistical estimator, and you can promise me two things about it. You can promise me that it's accurate with respect to the sample, and you can promise me that it's differentially private, then automatically you have the guarantee that it's accurate with respect to the distribution. Okay? The empirical average mechanism is perfectly accurate with respect to the sample, but it's not differentially private, and so it doesn't guarantee accuracy with respect to the distribution. If I just threw away the data and gave you random noise back, that would be perfectly differentially private, but it wouldn't give you accuracy with respect to the sample. And the claim is if you can manage to get both
with respect to the population.
with respect to the sample or the population. And what this is saying is that if you can somehow manage to give me both of these guarantees simultaneously, differential privacy and accuracy with respect to the sample, then you get accuracy with respect to the distribution for free. Okay, so you've got your data analyst. He's interacting with a statistical estimator. The statistical estimator really only has access to the data set. But if it's accurate and differentially private, then you can run your analyses as if your questions are being asked directly to the distribution. Okay, so let's say that a bit more formally. Okay, this is a theorem. I'll have a bibliography at the end. Sorry for on the last slide I actually have the papers written down. This is a theorem of a form we initially proved, but with parameters that are improved. So formally, if we've got a statistical estimator for adaptively chosen queries, then for any distribution over the data, if we've got a data set that's drawn IID from that distribution, then if the algorithm is differentially private with parameters epsilon and epsilon times delta, and if the algorithm is accurate with respect to the sample with parameters epsilon and epsilon times delta, then, ignoring constants, the algorithm is also epsilon delta accurate with respect to the distribution.
That's the point about your having these two multiplied together in points 1 and 2.
Yeah, so differential privacy has these two parameters, this multiplicative difference and this additive difference. Yeah, I need the additive difference here if I want epsilon delta accuracy. If I want that with probability 1 minus delta, my error is only epsilon in the end, then for how differentially private does my algorithm have to be? Well, I need that multiplicative change is at most e to the epsilon, and the additive change is at most epsilon times delta. Yeah.
Ignoring orders here is something you can do, I mean, you might have a large multiple of epsilon or delta in the. You ignore the orders as you do in the end.
You mean the constants here? Oh, you mean like, might this be a less interesting theorem if like the constant here is 10 to the 8th or something?
Yeah.
Yeah, certainly that would be the case. The constants here are not tiny, but not ridiculous either. And I would say that it is, these are relatively early results. I'm not going to assert that for, all or even many data analyses, this theorem is immediately practical. The constants are not so huge that I think it could not be practical in large data applications. That being said, these constants are not 1 or 2. They're sort of, meaningfully large constants. And I I think there's sort of lots of interesting work to be done making these theorems tighter. You know, they're not tight in terms of constants as far as I know.
I mean, delta is a probability, isn't it?
Yes, I mean.
Yeah, so it's bounded by 1, so you cannot. It's a multiple of this.
Oh, I mean, obviously, if you prefer, I could put the big O over here and have this be delta.
Yeah.
I mean, you know, if you want this to be 0.01 and there's a constant of 10 here, I can just divide by 10 here.
Okay, fine. Yeah. Okay, fine.
Other questions?
What's 2 mean with respect to the sample? Does that mean sort of that criteria you had before, but then you do want to replace the phi d?
Exactly. What I mean is that with probability, you know, 1 minus epsilon delta, the maximum error you get with respect to the empirical average should be epsilon.
So it's sort of you think some kind of lower limit would depend on the sample size and the estimator and things like that, right? In the sense that, like you say, with n equals 5, you can't do anything.
That's right. So, right, you might wonder, like, you know, how come, like, sample size, which seems like an extremely important parameter, is not coming up in this theorem, right? Well, this theorem has a hypothesis, right? We need, right, this is so far a theorem of the form, you know, like, if pigs can dance, horses can fly. This is meaningful only if I have such an algorithm that is both private and accurate on the sample. And as we saw from Adam's tutorial, those algorithms will have sample size requirements. In order for there to exist such an algorithm, I will need n to be sufficiently large. I'll give you a couple of instantiations of these things in a moment.
When n is sufficiently large, you actually might get the, with respect to the population, from the unperturbed
That's right.
value. So, because that's what you really need, right? You need that.
Yes. So in a couple of slides, by applying this theorem, I'll get some actual sample complexity bounds. Other questions? Okay, so I think I will not prove the theorem, although the proof is not difficult. I mean, it's on a few slides. The whole proof, easy peasy. Almost the whole proof. There we are. Okay, so let's apply this theorem and see what we can get. Okay, so we need something that's accurate, and we need something that's private. Okay, and remember, we saw the very simplest example of a differentially private algorithm that guarantees some accuracy with respect to the sample. That was just the simple Gaussian perturbation method that I showed you on a few slides ago, and that Adam talked about. So let's see what we can do by just plugging in the existence of that algorithm into our theorem and see what we get as a statistical estimator. Okay, so just independent Gaussian perturbation yields a statistical estimator, and this is extremely simple and computationally efficient, because literally all you're doing is perturbing the answers with Gaussian noise that can answer with 99% probability k queries with at most 1% error, where k can now be something on the order of n squared, the square of the size of the data set. Okay, so this is improving, remember, by a quadratic factor over the naive mechanism, the mechanism that just returns empirical averages. That one could only answer n queries like this. Okay, and this was, we did almost nothing. All we did was add Gaussian noise, and we have a quadratic improvement in the sort of power of our statistical estimator. It turns out that we've been studying, you know, this question in the differential privacy literature for a long time of how to answer a large number of statistical queries privately and accurately with respect to the sample. Okay, and if you plug in some of the state-of-the-art bounds from that literature, what you recover is the ability, is estimators, thank you, that have the ability to answer, again, nearly exponentially many queries, even though they're adaptively chosen. With a couple of caveats, though, because now the number of queries you can answer is exponential in the size of the database divided by log of the size of the data universe, which you should think of as the dimension of the space. So if you have extremely high dimensional data, this isn't such an interesting theorem. This theorem starts to be interesting when the size of your data is, you know, larger than the dimension of the data. Okay. And just a quick application. an efficient algorithm for reusing a holdout set. Okay, so suppose I've got a data set, and what I want to do is perform sort of data exploration on my training set, and I've got a separate holdout or validation set that I want to use to validate the results of my data exploration. Okay? Normally, if you want the guarantees of the holdout set, you can only use it once, because you want the holdout set to be independent of the questions you're asking to it. That's where it gets its statistical validity from. But I want a holdout set that I can reuse repeatedly, a reusable holdout. So here's an algorithm called threshold out. And it's really simple. Perhaps, I don't know how many people here can read Python. At ICML, it was a lot of people. But it's a really simple algorithm. Okay, you split your algorithm into a training set and a holdout set. And when the analyst, I'm describing now the statistical estimator. When an analyst asks a query, you evaluate it on both the training set and the holdout set. Okay? And you've got some threshold, and you've added noise, a little bit of noise to that threshold. And you ask, how big is the difference between the answer to this query on the training set and on the holdout set? And if the answer is small, if it's smaller than that noisy threshold, you give back the unperturbed answer on the training set. Only if that answer is large do you give back the answer from the holdout set, and then you perturb it with some Gaussian noise. Okay? And semantically, you should think of, when the answer is small between the training set and the holdout set, that's a round on which the analyst has not overfit. When the answer is large, that's a round on which the analyst has overfit, and you correct him by giving him the, safe answer from the holdout set. Okay, and roughly speaking, the guarantees of this algorithm, putting an asterisk here because the guarantees are a little more complicated than I've put on this slide. But roughly speaking, the guarantees of this algorithm are that you can ask a lot of queries to it. Unlike the Gaussian perturbation mechanism, the number of queries I can answer accurately is not just n squared. I can keep answering queries until the number of queries you happen to have asked that overfit the data set reaches n squared. So if you're an adversarial data analyst and you've managed to overfit every round, this sort of degrades to just the Gaussian perturbation mechanism. Every day I give you the answer on the holdout set with Gaussian noise. But if somehow you're doing something less adversarial, then maybe on most rounds you aren't overfitting, and this can keep answering questions for much longer. Okay. Now, I'm running out of time. This is a really simple algorithm, and so it means you can run some experiments on it. But these just illustrate the theory. So these are all on synthetic data, so I won't waste my remaining -1 minutes on them. I just want to point out that there are some generalizations beyond which I've talked about today. So I've talked about statistical queries, but it turns out that the same theorem holds for arbitrary queries that are low sensitivity, queries that, questions about the data that do not depend too heavily on any single individual. It turns out you can actually extend these results further to arbitrary events that you might care about. Any event that is unlikely to occur on a freshly sampled data set, independent of the questions you want to ask, is also unlikely to occur on a reuse of your data set, so long as the questions you're asking are differentially private functions of the data set. In particular, this lets you talk about p-values. And on the next few slides, I've got a bibliography you can read at your leisure, but otherwise, thank you very much.
It's a very short one. Regarding the initial motivation, there is a fashion among epidemiologists nowadays to use this, I think they call it, I don't remember the name, this analysis combining several analyses, meta-analysis,
Yeah.
they call it, where they combine several studies that have been published in order to get more results to support new conclusions. So what do you think about that?
Yeah, that's a great question. I think that's a great area for future research. Actually, when I talked about this stuff to Richard Burke, who's a statistician at Penn, he also suggested to look at meta-analysis. So I know very little about meta-analysis, but from my understanding, you want to get sort of better results by combining lots of existing studies, and to analyze these things, you make the assumption that the studies are all independent. And of course they are not. And it would be nice to be able to talk about meta-analyses in a more rigorous way using this kind of technology. Now, one problem is that once the study has, these results are all for sort of studies that have been conducted under the veil of differential privacy. And once you have a study out there that was not, the cat is sort of out of the bag. And I do not know how to go back and use these techniques ex post to reintroduce statistical validity. But I don't know how to, I think it would be very interesting to extend this line of work to say something intelligent about meta-analysis. But as far as I know, nobody's done that work yet.
And the other short question is that as long as, as people are using larger and larger samples due to big data collection and these kind of things, the overfitting problem becomes smaller, I think. Then do you think that this will be a vanishing problem in the end, or not?
Well, certainly overfitting becomes less of a problem as data becomes larger. You saw those in the sample complexity bounds. I mean, even without doing anything, using the empirical average mechanism, you can answer n queries correctly, and if n is really big, that might be enough. Now, in many applications, as data becomes larger, you also care more about small improvements. Google has an extremely large data set, which ads people click on, but Google's large enough that, forget about a 1% improvement, a 0.001% improvement in the click rate would be huge. So all of these things become smaller problems when data is very large, but if at the same time small errors also become larger problems, then you continue to care about the improved asymptotics.
I was just curious, can you show us one of the graphs and just quickly describe what it is you were going to show?
Sure, if I've got time.
For a few minutes.
Okay. Sure, so this is just a real simple experiment where a data analyst is doing something a little bit silly and gets into trouble if he uses the sort of standard holdout method, but not if he uses the method I proposed, or proposed in our paper and on the last slide. So the analyst is basically going to be performing stepwise variable selection. So this is a synthetic data example. We've got 20,000 rows of data, dimension 10,000, and every data point is labeled either -1 or +1. And the data analyst splits the data set in half into a training set, each of size n. And he's going to find the k variables that are most correlated with the class label. Okay? And then he's going to train a linear predictor on those k variables. Okay, so he's going to do model selection as a function of the data, and then train a linear predictor on those selected variables. And he's going to try to use the holdout set by only selecting a variable if it's correlated with the label, not just on the training set, but also on the holdout set. Okay, and we're going to try to find the best k. So here we've got an example where there really is no correlation at all between the labels and the data points. So any correlation you find is spurious. Now, on the standard holdout set, the data analyst, as he does this, overfits, and he overfits not just on the training set, but also on the holdout set. And so he has no way of detecting or correcting his overfitting. No model has better predictive power than 0.5, since there really is no correlation, but on the holdout set, it looks like he's found one. If he used the noisy holdout parameter, then on the holdout set, he would see the correct results, that he hadn't found any correlations. Now, on the contrary, if you do the same experiment where there really is some signal to detect, if 20 of the features really are correlated with the label, ideally you'd find them with this method. And when the data analyst does this with the standard holdout method, okay, he does find them, but then as he continues trying to add variables, the correlation looks like it improves, and if he then tries to find the best model, it looks like maybe adding 500 variables is the best thing. The green line is, again, the evaluation on the holdout set. But with threshold out, the green line tracks the actual true error, and the analyst can correctly detect the model size of 20 variables. That's the
So fresh is like a new.
fresh is like the true answer on the distribution. What you would get if you had like a third secret holdout set I hadn't told you about. Does that answer?
Yeah, that's good.
Great.
Great, I think that's.
All right. Thanks. Sorry for.